So far in our studies of noise, we've looked at the sources of noise, how noise comes about, and the impact of noise on some of our designs. Now we're going to look at the impact of noise when you actually have an amplifier in your system and how you can design for the lowest noise for your circuits to get the best signal to noise ratio. We've already found out that all resistors have the same thermal noise subject to the resistance. However, amplifiers can have different noise levels depending on the way that the amplifiers have been designed. They can have shot noise from their input bias currents. Some amplifiers use bias current cancellation, which introduces more noise. The different sizes of input transistors they use in the input stage of an amplifier can give rise to flicker noise. And also the type of transistors, whether it's bipolars or MOS or junction FETs, all have different characteristics regarding noise. In the case of bipolars, they have very low voltage noise, but can have relatively high current noise because the bias currents are quite large. MOS have very low input currents, so they have a very low noise current, but often a very large noise voltage associated with them. And junction FETs have got a low-ish noise voltage and a medium noise current. So the input stage of an amplifier is critical to the noise performance of the amplifier. In any design, an amplifier design, you can design for low noise current or you can design for low noise voltage. But you can never fix both because they are both interdependent of each other. In order for us to compare different types of amplifiers and different amplifier models, we need to use a simplified model to look at the effect of voltage noise on your circuit. Here we have one here. So on the left-hand side, we have the source, and associated with that source is a source resistance or a source impedance. It has a signal voltage, Vs, and associated with the source is a noise voltage, and we've called this VTH or Vthevenin. We've also got an amplifier model, and here we've modelled a noisy amplifier, a real amplifier, with a noiseless amplifier, a perfect amplifier, and a noise current and a noise voltage associated with it at the inputs. The noise voltage in the noisy amplifier model includes all the noise voltage sources associated with that amplifier lumped into one component or one element. And the units of that noise voltage are volts or nanovolts or microvolts per square root of hertz. In other words, the square root of bandwidth. And this gives us the noise voltage spectral density for the amplifier. Noise voltage for an amplifier is very often a function of frequency, and we'll look at that later on in the course. And we also have the noise current associated with the amplifier. It has the units of amps per square root of bandwidth. So let's look at the amplifier noise model in more detail. And we want to generate a single noise source, which is a combination of all the noise sources, and it makes the calculations easier. So we will take the squares of all the voltages or currents and the effect of the currents and add them together to form one input referred noise source. So let's first of all take our simple circuit, and our system gain, as we discovered in first year, is K, which is equal to the voltage gain multiplied by the input impedance of the amplifier divided by the source resistance plus the input impedance of the amplifier. That's a simple potential divider formed by RS and Zn. And we've got several noise sources combining to contribute here. The first one is the Vthev, which is the noise coming from the source. And if we take the square of all the numbers, we have the voltage at the output squared equals the gain squared times the potential divider factor squared times the voltage Vthev squared. And similarly, we can do the same calculation for Vn for the amplifier, and also for the current noise. So the output noise due to the In from the amplifier is the V out squared equals the gain squared multiplied by the parallel combination of the Zin, the input impedance, in parallel with the source impedance. Square that and we multiply that by current. So now we have a total noise voltage at the output, which is the gain squared times the potential divider squared, and that multiplies the Thevenin voltage plus the square of the Thevenin voltage plus the square of the noise voltage associated with the amplifier. And added to that is the square of the gain times the parallel combination of the input impedance in parallel with the source impedance, and all squared multiplied by the current. And working through the equations and dividing by system gain, we land up with an equation of the total input noise is equal to the square of the Thevenin noise, which is from the source, plus the square of the voltage noise from the amplifier, plus the current noise multiplied by the source resistance. And an interesting observation we can draw from this is that the actual input impedance of the amplifier is not important in this equation. It's actually only the source resistance that gives rise to the calculation of the total noise squared at the output of the amplifier. We can now look at our amplifier again, and we have our source. And in this example here, what we've done now is we've said we have they've got the noise, the signal source, Vs, in series with that a lumped noise source, which is due to all noise. And we have a noiseless amplifier and also a noiseless resistor. So we assume that Rs in this example here is noiseless, and the noise from Rs is actually combined into the Vni noise source on the left-hand side of a diagram. Now this analysis here is independent of the gain of the amplifier, and it is also independent of the amplifier input resistance, which means we can compare any amplifier we want using this model, and we don't need to worry about the differences in the design. It's just down to the figures and performance figures of the amplifier. We can also do this graphically, and I would recommend graphical analysis whenever you do noise, because it allows you to get a better feel for how you actually deal with the noise around your circuit. So first of all, let's look at our amplifier again, and here we have a noise voltage Vn from the amplifier, and we're going to assume that it is flat and constant across all frequencies that are of interest within the amplifier. And we're plotting here the log of the noise voltage on the vertical scale and the log of the source resistance along the horizontal scale. Now, if we look out at the effect of the source resistance on noise, we can now draw a second graph, which is the noise current multiplied by the source resistance. And that's a constant because it rises as In and Rs increases. So that would keep on going down here on the log scale and rise up as we increase the source resistance in this direction here. We can also add to this our Vthevenin, and this Vthevenin voltage here is purely dependent on the source resistance. And we know from our earlier calculations that noise voltage is proportional to the square root of source resistance. So we have a graph here which is dependent on the resistance, and we have a second line here which is dependent on the square root of resistance. So looking at these three different curves for a given amplifier, we can now surmise where the best position is and what the best source impedance choice would be for this given amplifier. And we find that the optimum source resistance for noise performance for a given amplifier is when the noise voltage divided by the noise current for the amplifier, which gives a noise resistance, is that point there. So we take the noise voltage from the datasheet, we divide it by the noise current from the datasheet, and we come up with that point there, which is the most appropriate point to operate an amplifier for lowest noise. At this point here, the amplifier will add the minimum noise to the signal when RS, the source resistance, is equal to the optimum resistance for feeding the amplifier. And this is the lowest you can possibly design an amplifier for the noise from a given amplifier. That's not to say that all amplifiers have the same noise. Each amplifier will have a different optimum R source point, but for a given amplifier, the best performance from the amplifier will be gained when the voltage noise divided by the current noise defines the source resistance. So now let's go on and look at some real amplifiers. And here we've taken an extract from an OPA 627 datasheet. You can go onto the datasheet, I've uploaded it onto Moodle, and you can look at the real curves. And what we have here is we actually have the noise curve for an OPA 627 plus a given resistance. And we've got our schematic drawing it up here in the corner. And our optimum point here is at this point here, when we calculate out that the noise resistance is equal to the noise voltage. Now, we've shown two amplifiers here, and the optimum for the OPA 27 gives us an optimum resistance of 7.5 k ohms, whereas the optimum point for the OPA 627 would give us a much higher source resistance optimum point of 2.8 mega ohms. We've now looked at some of the challenges in doing noise design for amplifiers. We'll next go on to look at some more amplifier circuits and do some more noise analysis with op-amps so you can get practiced for the questions that will appear in your final assessment. Thank you.